Good morning, everybody. My name is Bart Pernil. I am the replacement session chair because the one assigned unfortunately couldn't make it. Welcome. This is a new room for crypto, first session of crypto in the ILP. And we have 4 talks, and all the 4 talks will be presented in person. The first talk is entitled Cryptographic Treatment of Key Control Security in light of NIST SP 800-108. And to save some time, I will not read all the author names, but the presenter is Stefano Tesaro. Stefano.
All right. Thank you. Thank you very much for making it to the first talk and for finding the way into this new room. So I was not planning to read all of the name myself, although a couple of them are here in the room. It's a joint work with a number of collaborators. So you is here and Melton is here as well. And in case you're wondering why there's so many of us, this was a working group at a Dagstuhl workshop that took place 1.5 years ago. And this is the outcome of that work. And the focus of this work are key derivation functions, which are used to derive multiple keys from a single master key. And they are widely used in practice. And there's also different variants and standards covering them. For example, a construction I assume many of you know is HKDF, which is used to derive keys, multiple keys from a high entropy secret through a paradigm which is known as extract and expand. And a somewhat simpler object is standardized by NIST special publication 800-108, where the master secret is already uniform. So in some sense, this is the expand part of extract and expand only. And for this work, our results are going to apply to this second type of key derivation functions, although our formal framework will cover everything, including HKDF. So the way you should visualize this a little bit more graphically is that you have parties that agree on a key, and then their goal is to deterministically derive a number of other keys for different symmetric algorithms, such as encryption scheme, authentication schemes, and so on. And the way a KDF helps them in that is by providing an algorithm that takes as input this initial input key, as well as a label that specifies the use of the key, typically, some context information, which will typically be the users involved in this process, as well as a nonce, and so on, and then the desired length of the key. And then given these inputs, the KDF will output the key of the desired length. And of course, they can do this over and over to derive different keys. And the standard security requirement for KDF is being a good pseudorandom function in this context. So you want the derived keys to be computationally random and to look independent. For example, the PRF security of the NIST standard for special publication 800-108 was recently studied in concurrent work by Shen, Wang, and Gu. So here we have a different focus. We study a different security property, which is called key control security, which was first informally introduced in the latest revision of 800-108 after some technical feedback that pointed out some different type of insecurity in the construction. It's a different flavor of security notion. In particular, it's a known key security notion that protects us from insider attacks. And I'll tell you a little bit more soon what this is meant to cover. So in fact, our contributions here there's 2 contributions in our work. The first one is that we provide a security definition and a formal framework for key control security. The second one is that we use this framework to analyze the NIST standard, both in terms of provable security as well as cryptanalysis. Now, I will start by spending a few high-level words on what key control security is about, and then we will work towards an actual formal security definition that we will use to look at the standard. So prior to our work, really everything we had was a definition of the notion in English text as written in the standard. What he said there is that key control security is a property which is attained when we have the assurance that any set of colluding parties in the key derivation process, even with knowledge of the initial key, cannot manipulate the process in a way that forces a particular generated key to have a value which is detrimental to an application using it. Okay, so we have to think a little bit more about what this means. But this is how the property was formulated in the standard. And so to make this a little bit more concrete, we can imagine a specific use case of a key derivation function where we have now Alice and Bob agreeing on a key. And then let's say that Bob is responsible for picking a nonce, which is then used as context to derive a key using the key duration function for an encryption algorithm. And of course, a honest Bob will comply with the protocol and say, pick this nonce randomly. But a less honest Bob could deviate from the protocol and potentially pick this nonce maliciously, depending on the actual key the parties initially agreed upon. And the goal here is for Bob to pick a nonce maliciously so that the output of the key derivation function, when using that nonce as a context, will be forced to a bad value, to a value in a set of bad keys. So for example, this could be weak keys for the block cipher underlying the encryption algorithm being used. That would be a problem, as key control security implies that finding such a malicious nonce, even given knowledge of the key, should be infeasible for any reasonable notion of bad keys. And to show you why this was a problem, in the initial version of the NIST standard, let's look at the simplest key derivation function that is defined in the standard, which relies on the counter mode evaluation of a pseudo-random function where we are using the initial key as the secret key. Then we evaluate the PRF on input, the label, the context, the desired length, and then the counter as long as necessary to get enough key material for the desired key length. And let's look at the one block case just for simplicity. So here, one particular way to instantiate the PRF, which is presented in the standard, is by using CMAC, which is a variant of CBCMAC, where we will use a block cipher and then encode our label, context, and length and counter into the blocks of CMAC appropriately to get our PRF. And here's something that was pointed out by the Amazon cryptography team as part of their feedback to NIST for their key derivation standard, was that this construction allows an attack, which we will frame now as a violation of key control security. So in particular, given the input key, what an attacker can do is it can force to the output, it can find a particular context that will force the output to equal as any potential target value T. So this attack here will require 3 blocks, and the way the attack works is very simple. So we can initially we can fix the first part of the context. So the context will be spread across the 3 blocks. We're intentionally setting up things this way. So we will pick the first part of the context arbitrarily. This will fix the first CMAC block. Then we will pick the third part of the context also arbitrarily to fix the final block of CMAC. And then now what we can do, we can simply invert the block cipher on the target value. We know the key, and get this intermediate value Y. And then this in turn will allow us to get middle part of the context that will now satisfy that the evaluation of CMAC on the given key equals this target value T. So this is actually, in fact, a pre-image attack against CMAC in the known key setting, which we are turning into a pre-image attack against the corresponding key derivation. And I should point out that with a similar motivation to ours, the concurrent work by Shen Wang and Gu also studied pre-image security of special publication 800-108, and they also look at collision security for different reasons. I should also point out that after the feedback from Amazon, the NIST standard was revised to include key control security, and also some strengthened variants of the CMAC modes have been included that are aimed to prevent this type of attack. So here we also want to argue that it's really not only about pre-image security against a single target. So key control security really should target something more general. So it's also important in cases where there are exponentially many targets. So for example, if we were to look at the prior attack I just gave you, and we extend it to 2 blocks of output, and it easily translates into an attack that gives us a 256-bit key where the first half consists of zeros and the second half is arbitrary. This will also be problematic if, for example, you were to use that key with an Even-Mansur cipher where, for which such a key will be a weak key. And so it's not just about single targets. And more generally, we're really interested in covering adversaries that might adaptively choose some predicate that defines whatever application-specific bad keys are involved. And then we'll try to map the initial key through some context to some output key that satisfies this predicate. And we want this to be hard for any predicate that is sufficiently sparse. Of course, if all keys are bad, this is not very interesting. So now I want to use this to give you a formal definition. Okay, so I'm going to give you a definition first in the standard model, and then I'm going to talk about some subtleties in extending this to ideal models where everyone has access to an ideal oracle, such as a random oracle or an ideal cipher, because this is what we are going to need for our security proofs. And the way we think about defining key control security is as a multi-stage game, where we think of the process defining this initial input key as being malicious, as an initial stage adversary A1 that outputs that key, along with a desired key length, a label, and a predicate defining which keys are bad, and some additional state information. And then all of this is actually passed on to the second stage adversary, which is then going to output some context. And this adversary pair wins if the KDF evaluated on everything, in particular on this context, the output is such that it satisfies the predicate. Now, if you look at this game, you might wonder, first of all, why it's a two-stage game with passing everything on, and why is it even hard? In fact, it's very easy if you think about it to come up with an adversary that always wins. And to prevent that, we need to add some additional conditions that avoid trivial wins. And the first one is that we want to ensure that the key still has some entropy given everything else that is being fixed by the first stage adversary. And we do that by imposing an average mean, so a requirement on the average case mean entropy of the key portion of the output of the first adversary conditioned on everything else. So we require that to be at least some value k. And then, of course, the other one I've already mentioned is that we need to ensure that the predicate is sufficiently sparse. So the fraction of keys that maps to 1 should be at most some fraction delta. And so, for example, if the predicate would map all keys for which the first half is 0 to 1, then delta would be 2 to the minus L over 2. And we're not going to really say what's a good K, what's a good delta. We are targeting concrete security. Our bounds will depend on K and delta. Now, coming back to ideal models, well, the first thing we want to do is we want to give everyone, so the adversary and the KDF, access to an ideal oracle, such as a random oracle, an ideal cipher, or random permutation. Now, where's the subtlety? So the problem we encounter is in the first non-triviality condition. So now the key which is output by the adversary can potentially depend on the oracle. And so it could have just mean entropy because it's the output of the random oracle on evaluation 0. It's not very interesting. That's not real entropy. And so to do that, what we do here, it's one way of solving the problem, is we actually condition additionally on something else in our entropy requirement. What's that something else? Well, it's the transcript that includes all input outputs of queries made by the first stage adversaries to its oracle. This is actually not a new approach. So in a paper in a paper by Coretti, Dodes, Kartikeyan, and myself, we analyzed random number generators for oracle-dependent sources, and we had something similar to model that situation. And so this is the definition we are going to work with. And now what can we say about the standard? So let me first point out that I already mentioned counter mode, but the standard also covers a number of other constructions. In particular, there are two further modes for PRFs. One is a feedback mode. The other one is a double pipeline mode. And they both can be instantiated with HMAC if you want an hash-based instantiation, or with CMAC if you want a block cipher-based instantiation. And then there's another option, which is simply to rely on KMAC built from SHA-3, and that's sort of quite easy to get a KDF from that. And now here we have two sets of results, and I won't have time to give you the details in this talk length, and the proofs get rather involved, but I can tell you what the summary is. And we have a number of results for hash function based constructions that are actually proofs. So we upper bound the probability of an adversary winning these key control security games as a function of the entropy and the sparsity of the predicate. And these constructions are analyzed in the random oracle model. So we model the underlying hash function as a monolithic random oracle. So another parameter in these bounds, Q, is the number of random oracle queries by the adversary. And these bounds also depend on the hash length. And H and S is just the number of blocks to get the desired length. And overall, we see these bounds as good news, although most of them contain a birthday-like terms that you might be worrying about. The good news here is that the hash length will be at least 256 bits, so these birthday terms do not really matter if you target 128 bits of security. Now, this brings, of course, the question of what happens with block cipher-based instantiations if you want to use a block cipher that has 128-bit blocks. And here, our work has been mostly cryptanalysis. So we already knew from Amazon's feedback that the counter mode, I mentioned the attack before, but that extends also to feedback mode. With CMAC, we already knew constant time attacks against both of these constructions. We complement these with more attacks that essentially show birthday type attacks against everything else. So in particular, also the strengthened modes that have been introduced to bypass Amazon's initial attack are affected by something which is slightly harder than a birthday attack. There's some extra overhead cost. And again, these attacks are rather subtle and you don't quite get birthday because we really need to also deal with the fact of how the inputs are encoded and be very careful with how things are done in the standard. But if you're targeting 128 bits of security, then these constructions are not good enough. Okay, so this is actually everything I wanted to say on the technical end, but let me just finish by pointing out that at least on the theoretical end, this is a new notion. Also practically, this hasn't been considered really widely, except in the standard. And so of course, this comes with a number of open questions. So for the CMAC-based instantiations, again, I want to stress we do not have proofs. I expect them to be quite involved compared to the hash-based constructions. It would be good to verify that the attacks that we give are best possible. Another more general question, it's a new notion. We haven't really thought about what are best possible constructions. So in some sense, this comes as an afterthought. So if you were to build a KDF with key control security in mind, what's the best possible construction? Another thing I want to point out, this actually has been bugging us for a while, is that the analysis assumes, for the hash modes, assumes that the underlying hash function is a monolithic random oracle. Now, it would be nice to give an analysis based on a simpler primitive, like a kind of DL compression function on a permutation. It's not that easy. And also note that you cannot apply indifferentiability directly here because our game is a two-stage game, and we know that indifferentiability doesn't apply here. And finally, maybe that's the thing that has been bugging me the most. The attack is present. So the whole attack came up in the context of the standard. The standard covers this notion. It's a very appealing notion. It's something you might agree that a construction should satisfy. But at least I'm not aware of any real-world attack against a protocol that leverages it. I mean, maybe you can come up with something artificial, but it would be nice to investigate whether out there are protocols that are affected by violations of key control security. I think on the applied security side, that would be a very interesting question. All right, this is everything I wanted to say. So thank you for being here. And the full paper is on ePrint with a lot of more details. Thank you.
Thank you very much. It's time for a quick question. Gregor?
Maybe about the reword.
Can you use the mic, please? Yes.
Thank you very much for the talk.
Yeah.
About the reword text, you said like you can come up with artificial things that.
I mean, something like the example I gave, where I really, give responsibility to the user, to one user to come up with the nonce, and then that user alone can bias the nonce. But
why would he?
Yeah, so that's the question.
Okay.
I mean, okay, not as there was an incentive. I think once the user can, I mean, why not? The question is like, why would you design the protocol like that? And that's not, at least it doesn't seem implausible that out there people do that. I mean, the context option is there and it's meant to have a nonce in there. That's at least how it's specified in the standard. So I can envision that somewhere someone has used it in a way that the nonce can be influenced by a contribution. But if it's a counter, for example, instead of a random value, then there's not much to be done, right? Because everyone can agree on what the nonce is. And so I think that's more the concern. Like you will have to have something where the nonce can be picked by one particular party with some distribution, and then they violate that. That's definitely. But maybe someone at NIST in the room knows of a concrete attack, but at least we couldn't find it.
Okay, let's thank the speaker again. Thank you, Stefano. The second talk is entitled Integral Resistance of Block Ciphers with Key Widening by Modular Addition, joint work between Christoph Bayerle, Phil Hebborn, Gregor Leander, Jeffen Perehuda, and Gregor will give the talk.
Thank you very much. Thank you very much, Bart, for the introduction. Yeah, this is joint work with Christoph, Phil, and Jeffen. And actually, Jeffen was supposed to give the talk, a PhD student from Ukraine, but he didn't get a visa, so I have to do. To give you an idea of different directions. So as a motivation for this work, this is part of a bigger project that we are running in Bochum. And the idea is to give security arguments for symmetric cryptographic primitives, in particular block cipher. And for the state of the art, it is the case that there are many more arguments for linear and differential attacks and less for integral attacks. And this is what I want to do here, to improve upon security arguments against integral attacks. So the setting is with all attacks on symmetric ciphers, almost at least, is that we think about the block cipher, think about AES, and you take it in two parts, in R rounds, where you will have a distinguisher, some non-random property, and then S rounds that you use for key recovery. Yeah? So you would guess the last part of the key and compute backwards, and then depending on if the distinguisher holds or not, if this non-random property is observed or not, you would either say it's a good key or a bad key, and then this makes up your attack. And for this talk, the distinguisher will be an integral distinguisher, and I'll say in a second what this is supposed to mean. And I'm ignoring the key guessing part. So I'm only talking about the distinguisher. And the aim is to give arguments that allow us to argue about the non-existence of such an integral distinguisher. So I'm not trying to find new attacks, but rather argue that they don't exist. And this first part of the cipher will be called EK in the following slides. Okay, and so some history. The integral distinguishers was invented by Lars, and that's a picture of him on the age where he invented them, roughly, I guess. And he also asked me to say that he almost looks as young as on the picture. And it was originally an attack on AES, or AES-like designs, and we saw many improvements since then. Maybe the most important one are the division property and monomial prediction, and now very recently a geometric approach. And I'm going to use some of this in the talk. Wrong direction again. Okay, so what is an integral distinguisher? There are many different ways of capturing this, and I'm simplifying here for the sake of the talk. So the idea is that you find, given this block cipher EK, you find a set M, a subset of all possible plaintext that add up to 0. That's what the integral distinguisher is, and this sum is XOR. And actually, it would be enough for a distinguisher if this doesn't happen on the full state, but only on a few bits, or on linear combination of the bits. And now, instead of looking at the whole EK as a vectorial Boolean function, outputting this middle state, I'm thinking about the function that only outputs one bit. And this could be the linear combination of something, or think about the first bit of the ciphertext. And I want to argue that there is no such set M which gives 0 in the sum. Okay, so what I want to do, exactly what I say, I want to show that for any non-trivial set M, the sum is non-zero. Yeah, and what do I mean with non-zero? I mean it's non-zero as a function in the key. Yeah, so this depends on the key, and of course now it outputs only one bit, this F, so it's 0 often, but I want that there are keys which output 1 and there are keys which output 0. That's what I want. That would cover the resistant against this kind of attacks. And what this means is that what I'm actually looking at is an arbitrary linear combination of these functions. Right? So x is fixed, and then I have functions in the key, and they should not add up to the or zero function. And that's the same thing as saying I want this function that map the key to the ciphertext for one fixed plain text. I want all these functions, these 2 to the n functions, to be linear independent. That's what I have to show. Okay, that's what you need to show if you want to prove linear resistant against integral attacks. And now this is super complicated. Why is it complicated? Because you have a lot of functions, 2 to the n functions. So these are many, and of course you want them to be unstructured. So there's nothing you can use, no special property of these functions you can use, because if there would be, you would find another attack, right? It can only be a secure cipher if you cannot distinguish them from random functions. No? Okay, so how do we do this? And then a few years ago, we gave a first idea how you can do this in the case of using pre-Whitening keys, X or pre-Whitening keys. So what do I mean with this? So for now, I'm only describing, and actually most of the talk, I'm describing previous work. We have to explain a bit before coming to what we add in this work. Okay. So first, there are two things. We're going to look at the algebraic normal form of these functions, and then using Whitening keys to get this linear independence, kind of a boost in this linear independence. So what is the algebraic normal form? Every Boolean function can be written in this algebraic normal form as a polynomial in multiple variables. And because these fk actually is a family of functions, that means in the algebraic normal form, you can think of these coefficients as, again, polynomials in the key. Yeah? And so these pu are functions that, again, take the key as an input and output if this monomial appears or not in the algebraic normal form of the function. And the interesting thing is, if you know how to compute, or if you know a bit about Boolean function, then you know how to compute these. There's this Möbius transformation that allows you to compute the algebraic normal form, and it's actually a linear mapping. No? So it's linear and bijective, and that means that, okay, these functions which I want to show that they are linear independent, it's the same thing as showing these PUs are linear independent. No? So now I'm going to change my goal. I want to show that these functions that describe the coefficients in the algebraic normal form of my cipher, they are linear independent. And how do I do this? So each of them, a bit more on those, each of them is again a function. So each of them again has an algebraic normal form that I can write like this. And the good thing is that we can actually compute some of these values. Using this technique of monomial prediction and division property, we're actually able to compute, and that's not trivial, because again, it's a complicated function. We are able to compute some of these lambda uv values. And I'm not going to explain how, but that's computationally possible, but expensive. So what did I achieve so far? Nothing. Yeah, because instead of having these 2 to the n functions, which are unstructured, and easy to evaluate, I now have still 2 to the n functions, but they are much harder to evaluate. And I still want to show they are linear independent. But now the nice thing is that, so there's basically nothing we can do here. So we have to kind of add something more to be able to progress. And the idea is to think about what happens if you have an additional key that randomizes the input. And then, so if you look, so I'm denoting this new construction by f hat. So this is just you take the input XOR this additional key and then apply this function that we already have. And this again is a function, so I can write it as in its algebraic normal form, and now I call these coefficients QU. And what I want to show is I want to show that this new construction is integral resistant, resistant against integral attacks. So I want to show that these QUs are linear independent. That's the thing. And now the nice thing is this is much easier. Yeah? So this is what was in the previous work. So it's enough if from the original construction, these P functions, if you look at the ones which have maximum weight, so the U or W is an n-bit vector, and if all of these bits in this vector is 1 except 1, and you look of all n of these vectors, and these are linear independent, then from the new construction, everything is linear independent. So that's very nice, because now we only have n functions to this very mild assumption of an additional whitening key, and we get linear independence of everything. So why is this not enough? It's not enough because it's still n function and it's still computationally quite expensive. So it's possible, but it's not possible on, for example, on AES, we are not able to do. It's too expensive. Because it basically requires n square computations of these lambda u values. And it only captures XOR whitening keys. So the question is, so the problem is it's practically expensive and it has a limited scope because only capturing XOR whitening keys. And so what we do in this work is generalize this idea and to modular addition of whitening keys. And this nicely also gets rid of this practical expensive thing, kind of coincidence. Yeah? Okay, so now this is the new part. Took a long time to get there, but so and I want to. So the proof is not very technical, but technical. So I'm not going to go through the proof, but I try to give you an intuition why things are easier for modular addition. Okay. So what you basically have to study is how does this whitening key, this XOR of the whitening key or the modular addition of the whitening key affect the algebraic normal form of the function. That's what you kind of have to understand. And so for XOR, the formula is like this. So XOR K0 to U, you get this sum over all V which are smaller than U, smaller or equal to U. And smaller or equal means like the support of V is dominated by the support of U, right? And for XOR, there's a similar, very similar function formula. But now the exact shape is not so important, but the main thing is now you're going to sum over all V which are smaller than U as integers, smaller or equal to U as integers. And the basic idea is that in a nutshell, everything which is influenced in this formula, everything which appears in this formula will become linear independent. If you put the right conditions on your starting functions, and then all this will become independent. Okay. So why is this much better now? So if you want for the modular addition, why is this much better? Because you want if you want everything to be linear independent, so everything should be kind of influenced by what you get with this modular addition. And because the function you start with is going to be balanced, if it's a block cipher, it's a permutation, so this maximum coefficient will not be there. So you start with degree at most n-1. So this means this U is excluded. And so if we want to capture all the elements V, yeah, in the case of XOR, we really need these n-1 elements of weight n-1. Yeah? Because if you have less, then you will always be able to point at one V, which is not there in this expanded world. I'll manage, I think. Thank you very much. Okay. And what happens in the XOR case much nicer. So there, if you, it's enough to capture, it's enough to use this U as 2 to the n-2, and everything will be influenced by this. So everything will be linear independent, just if this one value is there. So what this means for the condition, much weaker condition and computationally cheaper. So in the picture, if you same situation as before, the only thing that changes is now you have modular addition at the input. And you do the same computation and using the formula before, what you can show is that, okay, now the only thing I have to ensure is that Fk, this original construction, has this polynomial of 2 to the n-1 non-zero, 2 to the n-2 non-zero, and then that automatically implies that you have integral resistance to all the QUs of this construction, including the modular addition, linear independent. So that's very nice. So we reduce from 2 to the n, not to n, but to 1. And then instead of the necessity to compute n square of these hard to compute coefficients, you only have to compute 1, which is much nicer. So what else? There's many more things in the paper that I'm not able to capture here. So the first thing is that we also use post-whitening keys to allow to not only study one of these Boolean functions, but any linear combination. And again, it can be shown that also in this case, it's enough to compute one coefficient. We also generalize to word-wise addition. So the XOR, the modular addition is not on the full state, but on parts, which is actually used more regular in actual designs. And actually, this gives a nice unified view, because what we study now is this construction where you have T words of S bits each, and you do a modular addition on these words for post and pre-whitening keys. And actually, the case if T equals N, so you have N words, which means N words of size 1, that's exactly XOR, and that's the previous case. And if T is 1, then you have only one big modular addition. That all falls into this general framework then. What we also consider, so, and that's a bit still an open question, but I think basically not possible to solve this question. So what we aim at is that this sum is non-zero. And that's what I said would give you a resistant against integral attacks. But if this would be, for example, a linear function in the key, it would also be broken, right? So what you actually want is that for any set M, this is a complicated expression in the key, which does not allow you to exploit any information. And one way to approximate this a bit is to say this should not have low degree. It should be a high degree function in the key. Of course, that's not enough. No, I can easily write down high degree functions, which are easy to invert, which would give me a lot of information about the key. But we are able to do this by introducing this disorder integral resistance, and nicely, actually, the previous work already gave exactly these results for quite high degree. But going beyond this, I think it's just not possible. I don't know how to capture it in a better way. Okay. And I think that's all I wanted to say. So maybe it's no surprise that modular addition gives you better security against integral attacks, because you can combine with very high degree functions, and that should help. But what is surprising, I think, is how nice things fit together in this setup. So capture more, and it also gets much more simple. And there's more in the paper. So if you're interested, the full proof, there are concrete examples how many rounds this actually gives you in kind of security until you get this integral resistance, with concrete examples linked to the data. And we also get some interesting observations on the inverse cipher, where it's not so clear by default that this gives you the same properties. And that's all I wanted to say. Thank you very much.
Thank you. Any questions for Gregor? So very concretely, if you would take the AES and you would replace the first addition by the first XOR by whitening by addition, would you get better security, or did you look at this?
So no, we did not look at this. I think you would end up with a number of rounds, which is resistant against integral attacks, but which is still not secure. So, and therefore, yes, this is not the limiting factor.
Okay, let's thank Gregor again. Thank you very much. So we move to the third talk of this session, entitled "The Exact Multi-User Security of Key Alternating Faisal Ciphers with a Single Permutation." A joint work between Yusuke Naito, Yu Sasaki, and Takeshi Sugawara, and you will give the talk.
Thank you for the introduction. So in this talk, we present about the cryptanalysis and the proofs of some block cipher construction. So to analyze security of block cipher construction, it is popular to generalize construction, because if the results are obtained for the generic construction, then any schemes belonging to that generalized class can be evaluated in the same way. So the goal is to derive the lower and upper bounds of the construction. And so by generic construction, I mean the example, I mean it's key alternating ciphers, or like some fatal ciphers. And at Eurocrypt 2024, by the same author, like with Naito-san and Sugawara-san, and evaluated key alternating ciphers. So so we believe that the problems have been solved for key alternating ciphers. So the next target is facial construction, because it has some internal structure in the facial ciphers. The analysis is more complicated. And by facial, we still have more several classes. The first one was a little bit later. This was proposed in 1986, so it was quite old. And so now the size of each branch is n bits. And the round function is secretly chosen random function. So this is quite generic. And so this is the permutation version of the reveal takeoff. So the round function is now replaced with some secret permutation. And several results are known in this construction. And the third one I'd like to mention is quite different from the previous, because now the round function is separated into the key addition followed by public function. And this was the first study was done in 2014. And so we have a big change in the security analysis, because now the adversaries, not only the from construction queries, I mean the conversion from P to C, they can evaluate this public function. So they can know like what input information goes to the output information. So the analysis becomes very complicated. And the last one, which is analyzed in this talk, is permutation version of the construction. But we have additional key addition after the permutation in each round. So eventually, so this can be said that even master construction is used in the run function of the facial cipher. And this was the study in the last year. And this was motivated by the fact that practical designs mostly adopt the public permutation, not function. But then why we need the post subkey? So then we first show that this is relevant to practical design, because if this is secure, then whitening plus like key followed by permutation is secure. So how to show it? So this is the construction we study in this paper, and this is the like a practical structure. For example, whitening key, and the round function is subkey addition followed by the permutation, public permutation. So if you want, for example, like ISO standard Camelier adapts this construction. So how to change it? Explaining all the details is a bit complicated. So I'd like to show that. So this is the target, and we apply the linear conversion to move the key to somebody else and just rename the level. And then we add 4 independent whitening keys. Then this can be viewed as this one. So the practical structure is just like this one added by 4 whitening keys. So in other words, if this is secure, then this is secure. So now we wanted to discuss this structure. So the possible research direction is to derive the tight bound. So of course, the proving the security is important, and it's also important to propose generic attacks matching the proven lower bound. And another direction is the multi-user security. So the adversaries should have been given access to multiple users having independent keys. And another is the number of permutations. So sorry, no, just moved. Yeah, in this slide, I just used the different permutation here. But in practice, like it's likely that same permutation is used in every round, and the same applies to the subkeys. So if those are like independent, then proof can be simple. But in the practical situation, those are just like single choices, and it's important to prove in a situation that the target is similar to the Fiat construction. And given that this is a comparison of the results, so we prove that our rounds of our KFP is secure up to the square root to the r minus 2n divided by r minus 1. And this is tight, and the proof was in a multi-user setting. And the construction is a single primitive, and not all the keys are identical, but we introduced that r minus 2 keys are correlated. Three keys are correlated, so r minus 2 keys are independent. So the previous work in the KFP is this one. So it applies to 5 rounds, and the bound is 2n divided by 3. And the model is like a single user, and all subkeys are independent. Compared to that, we show our proof works for any number of rounds, and the bound is this one. So if by assuming r is 5, this value is 3n over 4. So by just for 5 rounds, our proof is better than this one, but it works for any number of rounds, and like it's multi-user setting, single primitive, and independent subkeys. And okay, so for tightness, we need to discuss the attack. So best generic attacks is for 5 rounds. So it was done by impossible differential cryptanalysis. Says like this difference never propagates to this difference. So can be used to distinguish this construction with this queries. But I'd like to say that this type of attacks would be applicable when R becomes large, since like any differential propagation would be possible for large R. So we need a completely different approach to discuss the generic attacks for large R. Okay, so since I'm doing a lot for cryptanalysis, I would like to explain the new attacks. It just directly go into our approach. That is a meet in the middle attack. So the strategy is still to find a match with construction queries and the primitive queries. So we try to generate a pair that for some construction query, like the internal state values are already like queried by the primitive queries. So we call it the consistent tuple. So consistent tuple is like those tuples. So and sorry, the figures are just for 5 rounds. And to recover subkeys, we make it a pair with another construction query. So the meaning is by just like knowing that the plain text is L0, R0, and like this state value is W2, V2, it's impossible to recover those subkeys. So this makes it the analysis difficult. So to recover subkeys, we make the pair to another construction query and try to trace the differential propagation. Because in the differential propagation, the impact of subkeys is like negligible. So we still can continue the analysis. Okay, so for to make queries, because the complexity is 2 to the r minus 2 divided by r minus 1 n, So the number of queries, construction queries and primitive queries is this amount. But to do the queries, we make some structures. So for construction queries, most significant bits are fixed to constant, and we try all the possibilities in LSB. And for primitive queries, the positions are opposite. So this is important so that like all the subkeys can be recovered from the tags. And for construction queries, yes, yeah, we just query several sets of this form. And for primitive queries, we query this one for R-2 runs. Then if the number of actually with this amount of queries, we will expect match between the construction and the primitive queries. And I mean, I just give you some idea of the differential propagation. So for any combination of this one, we make it another pair with like L0 prime, R0 prime, and corresponding ciphertext output. Oh, by the way, the attack is information theoretic. So we just need to care the number of queries, and the time complexity is not relevant here. And so by making it pair, we can compute the difference here. Then this difference will propagate to this difference. So even though we have K1 and K2 here, we can continue the propagation, continue the trace of the propagation, because I mean subkits doesn't change the difference. And so if you know that one value is V2, then now we chose another construction queries in which the internal value is unknown. But because the first value is V2 and now the difference is delta 0, so we can compute the second value here. And then then by using primitive queries, we can make queries to get the corresponding output, and can compute the output difference here. Then this difference can propagate to another round even with the existence of the subkeys. The similar thing can happen, but because the value is like randomized in the second round, for the third round, there's no guarantee that this value is already queried by primitive queries. So it's just probabilistic that if we can get the corresponding output from these primitive queries. So this is a probabilistic event. So if it succeeds, then we can continue the analysis. But if we don't have primitive queries, then we just need to, I mean, it's like a failure of the attack. So we need to take another construction query to make it pair. And yeah, I mean, I don't explain all the details, but eventually the key can be recovered. And for proof approach, so the method is Patterson's coefficient H techniques. And particularly we use the resampling method, but needs to be customized for the this construction. The resampling method for any number of rounds was presented at the Eurocrypt 2024 for key alternating cipher. So key alternating cipher is this construction. So I explained the overview of the idea here. So in the proof, we define dummy internal values for each message and ciphertext pair by forward and backward sampling steps. So first we conduct some forward sampling. But at some moment, the sampled value would collide with previously defined values, and which may reveal some inconsistency. So this is that event. If this happens, then we discard several sampling results and then resume the sampling procedure from the backward. This is called inverse sampling. Then this doubles the possibility to avoid the bad event and increase the and allowed us to derive the tight bound for key alternating cipher. But now the construction is KFP derived here. And so we need to update the proof algorithm. So the difference between key alternating cipher and key alternating facial is for here, just by fixing those like R-1 primitives, internal values, and then it defines all the internal values. I mean, so this values will fix this one, and this values will fix one. So like all internal values are fixed. For the face cell, because like the facial cipher updates only half of the state in each round, just fixing R minus the internal values define all internal values. Okay, then the collision event, bad events we needed to consider is will increase. For key alternating cipher, we just key alternating cipher we just like consider the one collision event. The full state is already collide or not. But for facial cipher, there are 3 cases that the collision happens in the input of the undetermined, the first one in the undetermined 2 rounds, and the collision occurs in the output of the undetermined rounds, and then collision happens in the output of the second round of the undetermined rounds. So the analysis becomes a bit more complicated, and we give a new resampling algorithm for KFP with a 3 collision event. And this allows us to derive the Maltese bound. Okay, so that's the overview of the talk. So we provide tight security bound of facial KFP ciphers in the multi-user setting, single primitive, and R-2 correlated subkeys. And for the proof, we apply the resampling method. And for the attacks, we devise the new information theoretic variant of the meet in the middle attack. Yeah, that's my talk. Thank you.
Thank you. Any questions? So if not, let's thank the speaker again. Thank you very much. And that brings us to the final talk of this session, which is entitled Enhancing Provable Security and Efficiency of Permutation-Based DRBGs. Is joint work between Hui-Yuk Chung, Seonga Wang, Wigyom Kim, and Yu-Yong Lee. And Hui-Yuk will give the talk.
Okay, thank you for your introduction. And hello, my name is Hui-Yuk Chung. And in this presentation, I will talk about our paper about enhancing provable security and efficiency of the permutation-based random number generators. So first, I will start my talk about explaining what a deterministic random bit generator, the DRBG, means. A DRBG is a deterministic and stateful algorithm that generates randomness using some entropy inputs. So the entropy input is a string that is derived from some unpredictable events, such as interrupt timings or the timing of keystrokes. And such strings, entropy input, will be fed into a DRBG, and DRBG accumulates its entropy using the entropy input. And if sufficient entropy is accumulated in the DRBG, and it will generate some cryptographically secure pseudo-random bits. So it is a DRBG. And such DRBG has a very wide range of applications. It is a fundamental component for cryptographic protocols, such as generating cryptographic keys or initialization vectors. So in case where the cryptographically secure random strings are required, and they might be generated by the DRBG. So given such broader range of applications, many operating systems already implements a DRBG inside of them. So for example, Windows use some counter-based DRBG, and iOS use Fortuna, and Linux use some custom-designed DRBG. And such DRBG consists of the two components. The first one is refresh, and it is entropy accumulation function. So it takes the current state S and the entropy input I as an input and return the next state S prime. So the S prime is more random than the current state S due to the accumulation of entropy contained in the entropy input I. And the next one is next algorithm, and it is output generating function. So the next function will take S as an input, and it takes len as an input too. It is a required length of the output. And it will generate the next state S prime and the random number Z. Okay, so one of the most representative permutation-based DRBG is the sponge DRBG. And this is the refresh function of the sponge DRBG. And it has the n-bit state, which is represented as the sum of the R, which is the sponge rate, and the C, which is the sponge capacity. So accordingly, the SR is the R-bit most significant bits of the state, and SC is the C-bit least significant bits of the state. So the state is divided into the two parts. And the entropy input will be added to the SR, and the permutation P will mix the all state and generate the next state S prime. So this is the refresh function. And this is the next function. So it is output generating function, and it will generate the R-bit blocks of the output, like Z1 and Z2, by invoking the permutation multiple times. And it will utilize some feed forwarding structure. So this is the output generating function of sponge DRBG. And those DRBGs are analyzed in the robustness model. So it is essentially a distinguishing game. And the adversary should distinguish between the ideal world, where the truly random bits will be returned, and the real world, where the DRBG's output will be returned. So through some oracle queries, adversary wants to determine which word it is communicating with. But there is some points of the robustness model. It is an oracle get and set. So the adversary has some power to obtain a DRBG state through a get oracle, and it has the power of set the DRBG state through the set oracle. So it is quite powerful, but also it has some limitations. So in the oracle next star, which is inside the ideal word, it will generate the truly random bits only when the state contains some sufficient entropies. So if not, and it will return the real DRBG's output. So to distinguish between the two words, the adversary first needs to provide sufficient entropy to get some distinguishing information. So it is his limitation. And this is robustness model. And now I will gonna explain about our contribution. The first contribution is designing of post-DRBG. So our motivation is that the sponge DRBG has some suboptimal output rate. It is due to the per permutation call, it uses the R-bit output for each permutation call to P. So it cannot utilize the full output of the P, whether it can use only a portion of it. So it might be suboptimal. So to address this issue, we present some post-DRBG, which is parallel output sponge-based DRBG. And the design rationale is very simple. Like, we just unfold the sequential structure and make it parallel and add some counter on it. But applying this simple idea, we can now use the full permutations output as on DRBG's output. Okay, so in summary, the post-DRBG can utilize the full output of the permutation P, but the sponge DRBG can utilize only portion or bit of it. So in other words, the sponge DRBG might require n over the R times more permutation calls to generate the same amount of randomness. So the efficiency must be better in here. And interestingly, by our analysis, there are no loss of asymptotic security level compared to the sponge DRBG. So our design, post-DRBG, improves efficiency while preserving the bit security. And this is our comparison table. Vertical axis is the name of the scheme and our experimental settings. So sequential means a single core setting, and 4 cores means some multi-core settings. And the output length, horizontal axis is just an output length. And the numbers in the table is the time in milliseconds required to generate random numbers of the given axis. So now we focus on the sequential settings. And we might observe that the numbers in the sponge DRBG is 1.4 times larger than the post DRBG's numbers. But what is interesting here is that the catch-up permutation we use to experiment, the output of the permutation, is approximately 1.4 times larger than the sponge rate R. So the difference in the output rate is clearly reflected in this table. And this difference happens the same as in the multi-core settings too. Okay, and this is our first contribution. And our second contribution is to designing a new security reduction technique using an MREC and MPRES. And this is just an example of the real-world queries of the adversary. So note that the adversary can query any oracle in any order. So this is just an example. So just for an example, adversary may start its query by refresh, and next in this order. And if he made the same order of queries in the ideal world, and the next will be changed to the next star oracle. So it can be returned some truly random values. And it is the only difference between the two words. And previously, a researcher used some reduction techniques. And those reduction techniques requires to design some intermediate words. So this is our first intermediate words. And it responds to the first next oracle with the ideal words next star. And in other subsequent queries, it will behave identical to the real world. So to capture the distances between the real world and this intermediate word, they use some REC game. So the REC game is essentially a distinguishing game. And the starting start as 0 as chosen by the adversary. And the adversary should provide enough entropy through refresh calls. And the game will be ended with the next oracle calls, and the S and Z will be returned to each other. So the S and Z in the real world is generated through some DRBG operation, while in the ideal world, it is picked truly randomly. So adversary should distinguish between these two words. And just for some additional information, there is an EXT game, extraction game, which is almost same as a REC game, but without the next call. So it consists of only the refresh calls. And the next step is similar. They designed another intermediate word, which will answer the first and the second next query as in the ideal word, and the subsequent queries, it is identical to the real world. But there are some subtle differences here because the next star will return some random state. So this state is not controllable to the adversary. And we need another press game to capture these differences. And press game looks very similar to the REC game, but there are two key differences. So the starting state as 0 is chosen uniformly at random in here. And the adversary is now not required to provide enough entropy. And it is the differences. Okay. By repeatedly doing each step, we can obtain these pictures. So the distances between the real world and the ideal world is now measured by the sum of the advantage of these subgames. However, the previous approach has some problem because the security bound will not be tight in this case. It is because the p-square term will appear in a single REC game. And p-square term is just appearing from preventing some primitive oracles collisions. And there is a most Q1 REC game where the Q1 is the maximum number of next calls. So the Q1 will be multiplied to the p-square terms leading to the C over the 3-bit security. And it is not tight here. However, the p-square term is from preventing collision in the primitive quotes. And even if we think the whole entire robustness game, and we want to prevent primitive quotes collision, and it will be p-square term. So no reason to multiply Q1 in the entire robustness game. So the Q1 is solely derived from those reduction techniques, not inherently inside the primitive queries. And actually, our team already addressed this issue in AsiaCrypt 24 by deriving some multi-extraction MEXT technique. The idea is just simple. So do not consider each extraction gain like Q1 times, and only consider them once through the MEXT gain. So now we don't have to multiply Q1 in this time. But however, our technique cannot be applied to the permutation-based DRBGs because it has an invertible refresh. So extraction gain, the adversary chooses the starting state SR and SC, and the return value S prime will be given to the adversary. And the DRBG can now invert the permutation and check there is collision in the lower C bits, and he can win very trivially in EXT game. So we cannot use some EXT games in here. But as we already see, the rec game resolved this issue. So the rec game always consider refresh and next together. So it prevents the inverse queries because of this feed-forward structure. So adversary now needs to guess the blue lines, the value of the blue lines, to invert the permutation. And what is left is to design the multiple version of rec game. So we need to design the mrec game that treats the multiple sequences of rec game at once to avoid the Q1 term, and also for the precedent ring games. Okay. So by using that reduction technique, we can improve the security bound of sponge DRBG from C over the 3-bit security to C over the 2-bit security. And also, we proposed the post-DRBG which enhances the output efficiency and has the same amount of security level as sponge DRBG. And also, we proposed some matching attacks and prove that our bounds are tight. So thank you for your attention.
Thank you very much. Any questions? John? Can you maybe use the microphone for the remote audience?
So in the model that you're considering, you allow an attacker to set the internal state of the DRBG.
Yes.
That seems like a very strong assumption,
Yes.
right? Do you have can you think of cases where an attacker would be able to set the state of the DRBG? Because compromises, I think, have to be part of the model, but the power to set the thing matter. That seems quite powerful, and that leads to in the NIST DRBGs having an instantiate function and a receive function instead of just a refresh. So I'm just curious about that.
So it is hard to imagine the real world attacks using some set abilities. But I think the original designers of robustness game just put them in their model to make the security model strong. So there are some possibilities too. The adversary might change only a 1 bit of state or not. So the set oracle will capture those attacks more powerfully. So
Thank you.
yeah, thank you.
If there's no other questions, let's thank all the speakers of this session. Thank you very much. So we now have a coffee break back at USAN, and we start again at 11:10. And by the way, the symmetric key people, there will be a cryptanalysis session in ILP 1302. Enjoy your coffee break.